Hello, my name is Niall Maguire. I am a fourth year PhD student at the University of Strathclyde, and today I'll be walking you through our CHI 2026 late-breaking work paper titled Towards Preemptive Physiological Error Classification Within Airborne Environments. And this was co-authored by our colleague Jacob Green over at BA Systems and my supervisor Dr. Yashar Mushfeghi. So one of the fundamental issues that aviation and pilot safety is facing currently is that 70 to 80% of all aviation accidents are attributed to human error. This is problematic as current safety systems are fundamentally reactive, that being that the error needs to occur before any sort of intervention is able to be enacted. Where also post-incident analysis can't actually prevent errors in real time, which is a shame, as that then means that the error occurs and the likelihood is that the accident is actioned upon. Now, one of the major solutions to this has been the use of physiological methods to try and predict and detect errors before they actually occur, where some research has shown success in this area, achieving up to 75 to 80% accuracy using physiological methods to actually predict errors. However, one of the major limitations is this is only being conducted within lab scenarios. Now, on top of this, the issue is, well, as soon as you translate those results into, say, actual aviation and flight conditions, you have problems such as motion artifacts, also G-forces, degrading signals in operational environments, and so no prior study has actually validated multimodal preemptive detection across progressive flight conditions. So what is the gap that our research is trying to fill? Well, without any evidence that predictive physiological markers remain detectable and actionable under real-world aviation conditions, the development of these kind of systems remains speculative at best, and so our work helps to address this gap. So to do so, we needed data from actual flight trials and pilots, where we could then assess whether they committed errors and attempt to predict them from the physiological data. So for this, we had 9 commercial pilots take part in our trials. Each of them was equipped with a G-Tech EEG headset, which contained 24 channels sampled at 256 Hz, where also 4 of the participants were equipped with the Tobii eye tracking glasses. The reason that the other 6 weren't was due to the fact that they required glasses to fly and operate the aircraft. So for each of our trial sessions, we had an initial baseline condition that was conducted within lab settings to get the participants familiar with the trial. This involved a low, medium and high difficulty challenge, which we'll talk about in the next slide. Following this was the actual airborne stages, where the first flight condition was straight and level flight. This was aiming to mimic ideal flight scenarios, but then we also, following that, exposed the pilots to a 2G flight condition, where they maintain a 2G spiral to simulate varying forces of gravity, as well as rougher flight conditions. Now, during the actual flight trials themselves, the task that we had pilots complete was the impact tool, which was a tablet-based device where the pilots had to complete a low difficulty trial, a medium difficulty trial, and high difficulty trial. And within the impact tool, it's a multi-session task where you have air threat detection, so tagging air threats as they come on and off a screen, radio communications, which tells you which air threats to tag as friendly and hostile. You also have ground threats passing by at the same time, operates the same as the air threats, where you just have to designate who's friendly and who's not. And then you also have a warning panel, which pops up in a randomized condition to simulate actual warnings that a pilot might experience during flight. Now, to maintain ecological validity, we also randomized the order of low, medium and high difficulty, so it wasn't sequential. So a trial could start out on high and end in low, and vice versa. Now, after collecting the physiological data from each of the pilots, we experimented with different temporal training strategies. Firstly was the discrete windowing strategy, where 10 independent 1-second segments were used to train each of our models, which we'll talk about in the next slide. But then we also use a cumulative windowing strategy, which aggregates from a given point up to the error onset, and attempting to simulate real-time operation. As I mentioned, each of these windows are then used to train and evaluate 3 classification models to predict if an error will occur at each of these varying processing time windows. For this we had 3 models, the support vector machine, a random forest model, and a multi-layer perceptron neural model, where each of them was trained on an 80-10-10 validation test split, where the final results were pulled from each of the different models. So going into our results after training and evaluating the models, what we have here is the EEG classification performance, where we very clearly see an 88.7% F1 score achieved 9 seconds pre-error, which far exceeds the 2 to 4 second windows reported in prior work, and also remains significantly above chance level at p less than 0.001 across the entire 10-second window. Also interesting to note is we see that cumulative windowing consistently outperforms discrete windowing, overall seeing a 3.2% average increase in F1, which helps to confirm that temporal context does help to improve overall prediction performance. Now moving on to our eye tracking classification performance, we see a peak performance in F1 score of 78% at the 2 second pre-error, with secondary peaks at 9, 7 and 4 seconds. We do see greater temporal variability than EEG, but statistically significant again, with p less than 0.05 across most time points. Again, we also see the benefits from the cumulative windowing integration, which actually benefits more so than EEG. We see an improvement of 4.1%, suggesting that ocular motor patterns require longer windows to potentially merge, allowing the model to project errors before they occur. So, in conclusion, we established that neurophysiological signals can preemptively predict pilot errors up to 10 seconds before behavioural manifestations in actual live flight conditions. EEG-based classification remains robust to motion artifacts, electromagnetic interference, and gravitational stress across progressive, demanding flight environments. And lastly, cumulative temporal integration consistently outperforms discrete windowing, demonstrating that physiological monitoring systems benefit from memory of preceding cognitive states. We have our social medias for NeuraSearch Lab and the QR codes there. And if you'd like to get in touch with myself or my supervisor, Dr. Yashar Masregi, our emails are also located on screen. Thank you for watching.